Hi, Year 12. We are going to take a look now at a new topic. I know we're going rather quickly through all of this, but you're going to spend plenty of time going back over the stuff we've done, I'm sure, in Year 13. But I think it'd be good to start on some aromatic chemistry, and then on Friday we can have a look over the stuff we did at the start of the week, and we can have a look through some of this stuff as well. So, aromatic chemistry. Um, this is quite a broad area of chemistry, but for Year 12, for A level, it's focused on the chemistry of benzene. Now, benzene is the most important unit or molecule within aromatic chemistry, and we normally represent it like so. So the benzene, this is a benzene ring. Benzene exists as a molecule on its own. This is C6H6. There is one hydrogen bonded at each of these carbons here in the hexagonal shape. But it also appears in huge numbers of molecules, in larger molecules. So if you look up, for example, the structure of paracetamol, paracetamol has a benzene ring in its structure. So it comes up all over the place. And aromatic chemicals are ones with this unit in here. It's called a delocalized ring. So these are delocalized ring of electrons. So we should be very familiar with the idea of delocalized electrons. You've seen them in your GCSE and in your A level in the context of free moving electrons in a metal. So they're not as free moving as the electrons in a metal that are free to move throughout the whole structure. These electrons are delocalized around the whole molecule. So we've got 6 electrons, one from each of the carbons in the ring. 6 electrons delocalized in this thing, and that's known as aromaticity, and it forms an aromatic ring and structures molecules with a delocalized ring of electrons are called aromatic, with benzene being the main one. So this is the main structure we're going to use to represent it. You could use the sort of displayed formula with the C's in there, but you'll almost never see that, and you won't be asked to draw that. So just the hexagon on its own, without the hydrogens drawn on, is how you're going to see benzene 99 times out of 100 in the context of A level. Now, these are also benzene and its derivatives, and all these ones with aromatics. They're also known as arenes. So that's a term for molecules with an aromatic ring in them. This is in contrast to aliphatic. So aliphatic chemicals, this is basically everything else, and that's what we've been working on for the whole of your chemistry since you started it. All these organic molecules they're aliphatic, the ones that you've seen. Ones that have the aromatic ring, then they're known as aromatic, or they are arenes, so that we can pretty much break down organic chemistry into the arenes and aliphatic chemicals. Now, one of the things they're going to very quickly move on to, and it will very frequently come up in exams, is something called the Kekulé structure. Now, chemists knew about benzene. They knew it was C6H6, and they spent a very, very long time trying to work out its structure. As you can maybe imagine, if I asked you to, if I told you there was something C6H6 and asked you to draw structures of it before coming across this here, you'd probably find loads and loads of different things, loads of different structures that were C6H6. And it took chemists a very long time to work things out. They did eventually work out that it was a ring. Realised, well, from the number of missing hydrogens, it probably had 3 double bonds. And the structure named after a scientist with the surname Kekulé was this structure here, and you'll see this very, very frequently past A level. So actually, this structure here, at university, never used it. I think chemists essentially recognise that this is much more correct. We'll come into why, but it's awkward to use. Whereas the Kekulé structure is actually far more commonly used up at universities and in academia, because it's actually much easier to use. But the Kekulé structure, this would be cyclohexane 1. We've got carbon 1, 2, 3, Actually, I've numbered those incorrectly. I'm going to go the other way. 1, 2, 3, 4, 5, 6. So it's cyclohexyl 1, 3, 5 triene. So that would be the systematic name for what we call the Kekule structure. So it's very, very close to reality. It's very useful, and it's also sort of a historical position on the way towards a better knowledge of the structure of benzene. Now we'll pause in terms of the Kekule structure. We'll look at in a bit more depth the structure of benzene and compared to the actual structure compared to Kekule structure, and then we need to kind of contrast them a little bit. So the actual structure of benzene is firstly it's a planar molecule. So if I draw the carbons out, sort of from a side-on view, they form a flat hexagon. So that is hexagonal in shape, and each carbon is trigonal planar. So it's 120 degrees around in each of these bonds. So it's 120 degrees between the carbons, between the CC bond and the CH bond. So it's planar and in a regular hexagon shape. There we go. Now, this is basically part of the structure of graphite, or the graphene sheet. So a graphene sheet, which makes up, if you stack lots of them on top of each other, you make graphite. Is a whole bunch of these hexagons that are all connected together. Now, each of these carbons only has 3 bonds, leaving it with 1 electron that sits in a p orbital, and the p orbital is the one that points up and down, like so. Now, each of those sits like so in the dumbbell shape that the p orbital has. Now, they're not going to stay just like that. These will interact with each other. So all the ones on the top overlap with each other, and then all the ones on the bottom overlap with each other. And what we end up with is a ring of delocalized electrons above and below. And this is where it starts to get very, very my artistic skills do not line up with how difficult this diagram is to draw. Unfortunately, I do not have sort of access to video editing to put a nice image in for you, but I suggest you go on Google and look up bonding in benzene. I'll see about attaching a picture to your assignment. But if we've got the hexagonal shape, this is like a side-on view, not from the top, and then you've got a ring of electrons above and a ring of electrons below. So you've got a lot of electron density above and below the plane of that benzene ring. So they're delocalized within that ring. The electrons in this regular sigma bond here, regular single bond, sigma bond, those aren't delocalized. They're fixed in position. The ones in the CHs, those are also regular normal sigma bonds. They are they're completely localized. They're not delocalized. It's the electrons in this which is a sort of form of pi bonding. So this ring of delocalized electrons is a form of pi bonding. They will very occasionally ask about that. So you've got a big delocalized pi system of pi bonding formed from p orbitals that are side on, whereas when they are delocalized throughout that whole ring, whereas these regular electrons in the normal sigma bonds, they are localized. So if we then think about why we can show that Kekule structure is not completely correct, is to consider what the shape of the molecule would be if it did follow the Kekule structure. Now, we'd expect the Kekule structure to be planar. We've got the double bonds, and around these carbons with the 3 bonds, we would expect them to be trigonal planar, just like it is around a carbon in an alkene. It's trigonal planar around that carbon, and we'd expect that for each of these carbons here, and so we'd expect the flat hexagon. So that matches, but you need to think about the strengths of these bonds and the lengths of these bonds. Now, in benzene, each bond is the same length. So if I'll give it a length I'll just say it's X. You could look up the value, but that's not important. And we'd expect each of the length of these bonds to be identical from each other. So we'd expect it to be a completely regular hexagon. However, in the calculate structure, the double bonds, in an alkene, the double bond, the CC double bond, is quite significantly shorter than a regular CC single bond. So if we take an alkane, we'll call that length Y, and this length X. X is quite a lot shorter. It's not half, but it's quite a lot shorter. I think it's somewhere between like 0.6 or 0.7 of this, so sort of 60-70% the length of that CC single bond. So you'd have these bonds being, you had short bond, long bond, short bond, long bond, short bond, and it would be a really irregular shape. It would still be planar, but it wouldn't be a regular hexagon. And we know it's a regular hexagon, so it doesn't quite work.